All right, so this will be a video about, oops, what happened in here? Phase, locked, loops, PLLs. All right, before I talk about the PLLs, let me discuss a few things in here. All right, so first, I'm going to discuss VCO. So here's what we call a voltage controlled. So before I even talk about phase locked loop, let's talk about a voltage controlled oscillator. A voltage-controlled oscillator is first and foremost an oscillator, which means it outputs a periodic signal that is an AC. So this is VO of t, right? Now, this will be always periodic. So it's a pattern that repeats. For sake of discussion, I'm going to assume that this is just a nice square waveform that is either zero or high. It doesn't have to be this way, but for now, let's just consider this case. Okay? All right. So this is the period, and obviously the frequency is simply 1 over t. All right, so this is my voltage-controlled oscillator. So I'm assuming output's a square waveform. It doesn't have to be a square waveform, but again, just to simplify the discussion, and then we're going to go to the general case where it is any oscillation. It doesn't have to be a square waveform. All right, moving on here. The VCO has a DC that goes in. All right, here's how the VCO works. If this input is equal to 0, then this one will output at a frequency, let's call it T0. So T0 is the period of the output of the TCO when Vn equals 0. Right? T0 means that it has a frequency F0. Right? Now, if we start increasing Vn, so Vn starts becoming positive, what happens to the frequency out of this thing? Well, we're going to output the same pattern, except that the frequency of this signal in here starts doing what? Going up, which pretty much means that now we get something like this. Okay? All right, so this is how a VCO works. Now, I'm going to just assume that we're going to represent in here the frequency of our output signal. This is the frequency of the voltage coming out of the VCO as a function of Vn. When Vn is equal to 0, this one will always output something. So the oscillator will output a square waveform even if Vn is equal to 0. There is no possibility for Vn to be negative, right? As Vn starts going up, what happens? Well, the VCO starts outputting a square waveform, but the difference now is that its frequency is going up, something like this. So you can simply say that the frequency of the signal out of the oscillator is F0 plus some constant times Vn. Now this constant here is definitely in hertz per volt. All right, per volts. That's what this constant is. You multiply it by this voltage, the voltage and the voltage cancel out, and then we just add a frequency to it. Right? This is pretty much how it looks like. Now, some VCOs have this curve that looks something like this. The curve starts at what? 0. So this is the frequency out of the signal coming out of the VCO, and this is the voltage at the input. What this says is that F of the VCO is simply some sort of constant times what? Vn, which means when Vn is equal to 0, F is equal to 0, there's no oscillation. Some of them look like this. Some of them even look something like this. Instead of being a straight line, it might be a complex curve, something like this. All right, so this is the frequency of the VCO as a function of Vn. Now, it's not very easy here to put these into equation, but what is important is that as Vn goes up, so does the what? The frequency. And it has to be what we call monotonic. What does it mean, monotonic? Always increasing, so it never ever decreases. If it's not monotonic, then we cannot stabilize the PLL. All right, so the PLL will never ever lock. In fact, it will go out of whack fairly quickly. And what does it monotonic? If V in goes up, F always goes up. So there's no part of it where it comes down and then goes up. So this is not allowed. If you have a signal like this signal is not monotonic. All right, monotonic simply means always increasing or always what? Decreasing. Whereas this one here, there's an increase, a decrease, and then an increase again. So this is not monotonic. Okay, so this is as for the VCO. All right, now we're going to take a look at a circuit called a phase detector. And, all right, or phase difference, phase detection, phase difference. All right, so we're going to call it a phase detector. All right, so here's what we're going to do. We're going to feed it two signals. This signal, we're going to call it VA of t. It's also periodic or square waveform. And then VB of t. VB of t. What does the phase detector do? Well, we're going to assume that everything is a square waveform. All right, so by the way, this is not too complicated to build. It really is not complicated to build. I'm going to show you an example in just a moment. But for now, let's just see how it works. Well, imagine that VA of t is a square waveform, something like this. Right? And VB of t is something like this. So notice something interesting. They don't have the same what? Frequency. All right? Now, as soon as these two are fed to the phase detector, let's just say that it triggers on what? Positive edges. When it sees this positive edge in here, what does the output of the phase detector? Now, the output of the phase detector is called the error. So I'm going to just call it E of t. So this is the error. So how does E of t look like? All right, well, it's going to be 0. And here it's going to go to a high. And it's going to remain at a high till we hit the next what? High here. Right? And then it goes what? Low. And then it's going to wait for the next high here. All right. By the way, this high was ignored. Right? It has detected this high. This high was ignored because we did not get a high on VB. All right. So please understand what's going on. It triggered on the first what? High. The signal went high, and it stays high till we get a high on VB. All right. If there's actually, it does not ignore this one, but it just maintained it at high. This is not ignored. So this triggers a high. This maintains it a high. And this high does what? Resets E. And then when we get another high here, this one goes what? High again. All right. This high confirms it. This high confirms it. And then this high does what? Resets it. And then the next high, it goes high. So what can we say about E of t? Well, we can say that E of t spends most of its time what? High. So it spends a lot of time high and very little time what? Low. Why? Because I get a lot of positive edges in here that maintain this signal high, and only now and then a positive edge on VBOT that forces low. So these positive edges forces the signal to go low, and these positive edges forces the signal to be high. This one forced it to be high, and we saw it because it was low and high. This one also tries to force it high, but it's already high. This one forces it high, but it's already high, and this one forced it low. And then this one forced it what? High again. All right, so this is E of t. So notice that if there's a difference of frequency between the two, right? E of t is almost all the time high. So E of t looks something like this. I'm going to just draw your E of t. So let's just say E of t spends most of its time what? High. Let's say that this is 10 volts, right? And this is 0 volts. If we average this E of t, well, it's going to be a fairly high voltage, fairly close to what? 10 volts. So the average would be, this is the time, by the way, also this is the time. So if we take this signal and average it, most of the time it is pretty much what? It is pretty much what? High. And fairly close to 10 volts, almost 10 volts. I mean, these will reduce a little bit of this average, but they reduce so little that it's practically, maybe it's 9.7, 9.8 volts. Right, that's it. Now let's assume that these two signals are almost in phase and they have almost the same what? Frequency. All right. So here's what we're going to do. We're going to assume that they're almost in phase. Right, so this is VA of t. Boom, boom, boom. Okay, something like this. Okay. All right, so this is VB of t. We're going to assume that VB of t is fairly what? All right, so here it is. Oops. So they are, not only do they have the same frequency, but they're almost in phase. Not 100% in phase, but they're almost in phase. All right, so this is positive edge, positive edge, positive edge, positive edge, positive. Now remember how the phase detector works. When I have a positive edge in here, this goes high. When I have a positive edge in here, this goes low. That's it. It only triggers on positive edges. So positive edges of VA force this to go high. Positive edges of B forces this to go low. Right? So this forces this to go high. And high can be a 5 volt, it can be a 3 volt, it can be a 10 volt, it doesn't really matter. And a positive edge in here forces this thing to go low. Got it? All right, let's come back in here. All right, so this is E of t. When this positive edge triggered, E of t goes what? High. But almost immediately, this one forces it to go what? Low. This one forces it to go high. That one forces it to go low. This one forces it to go high. That one forces it to go low. Goes high and almost immediately goes what? Low. Goes high and almost immediately goes what? Low. So now we can see that when the two signals have the same frequency and the difference is phase is fairly small, E of t spends most of its time what? Low. And when we average it, right, assuming that this is the time, or this is just the zero, all right, so E of t, the average is practically what? Very, very small, practically zero. So there's a big contrast between this case and that case. Okay? All right. All right, so now how do I get the average of this signal? Well, again, I'm glad you asked. Here's how we can get the average of this signal. So this is E of t. This is what we call the error. So if E of t looks something like this, all we need is take this signal and feed it into an RC, a low-pass filter. All right, so if this signal is fed into a low-pass filter, basically an RC circuit, and we get the output out of here, right? What happens? The capacitor charges, so this is E, I'm going to call it E average. So E average is simply E at the output of the RC circuit. So it charges, and then so the capacitor does what? Charges. So we did. And then it what? Discharges. Charges, discharges, charges, discharges, charges, discharges. And this is pretty much what? 0 volts. So we notice something interesting in here. The average is practically a what? A DC. It's not really DC, but it definitely is always above what? Zero. There's still a what? A ripple. Now, how can we decrease that ripple? All we need is just make this capacitor slightly what? Larger. If we make the capacitor slightly larger, then this is what's going to happen. Let me just now delete this thing. All right, let's just. All right, so I'm deleting a lot of stuff in there, but there's nothing I can do about it. All right, so this is the 0. And if this capacitor has gone up, maybe by putting 2 or 3 or 4 of them in parallel, here's how the average looks like. Right. It charges fairly what? Slowly. And this charges fairly what? Slowly. Charges fairly slowly. This charges fairly slowly. So you can see now that the ripple is much, much what? Less pronounced. And we can say that E average is practically a what? DC voltage. It's not 100% DC, but practically DC. Now we can feed this into a voltage regulator that will flatten it, right? But that would make the circuit slightly more expensive. So it's not really necessary. All right. So with all of these pieces in mind, let's now take our phase detector. All right. And let's say that I'm feeding it here by the way, this voltage is called V reference. So this is VA of t. And this voltage is known as the feedback voltage V of t. We're going to assume that both of them are square waveforms, right? So let's say that this is how they look like, all right? So the reference voltage has a much, much higher frequency than the feedback. So this is the reference voltage, and this is the feedback voltage. So it's obvious that they are not at the same what? Frequency, all right? So the frequency of the feedback is much smaller than that one, right? So this is my phase detector. Now the phase detector will go high here. So this is my air voltage, E of t. So how does E of t look like? Well, here's how E of t looks like. All right, it goes high here. This one reinforces the high, and then it goes low here. And then again, it goes high here, and this reinforces it. This one reinforces it, and it goes low until the next high here. Okay? So it's obvious that this is a signal that spends a lot of its time what? High. So if we average it, if we average this by running it through a low pass filter, assuming that this is a 0 and this is 10 volts, it's going to be a fairly high voltage, 9 point something. Right? It's not really a straight line. It fluctuates a little bit, but that fluctuation is not relevant. So if we feed it to a signal like this, and we take this and we run it through a sort of a RC circuit, just a low pass filter, right? I get here E average. And since this E average is fairly high, if we feed it into a VCO, what does the VCO do? Well, it's going to output a signal whose frequency is going to go up. So this is V of t. We're going to simply take this, and this is our feedback. So we're assuming that when we turned on the system, right, the VCO was outputting a square waveform at a fairly low frequency. This one here. So this is the output of the VCO. So VFB, so the feedback is in this case the same as the what? The output of the VCO. So originally, the output of the VCO is pretty what? The frequency of the square waveform coming out of the VCO is pretty what? Low frequency. But when this signal here is fed through a phase detector, I'm getting in here a square waveform where it spends most of its time what? High. Something like this. Most of its time is spent high. if we average it, what do I get in here? I get a voltage that is fairly what? High. So this is E average, right, over time, and this is E over time. And since this is a high voltage, that's the V into the VCO. So what does the VCO do to this output? The frequency of this starts doing what? Going up. As it goes up, what happens? Well, these pulses in here start doing what? Becoming shorter and shorter. And this is now what I have. I will get to a point where this is, the V reference does not change, by the way. It is always at the same frequency. What changes is the feedback. So this is my reference voltage, right, or reference signal. Now this is the what? The feedback. What happened in the feedback is that now its frequency has what? Gone up, something like this. And what is now E? Well, E now goes high here and almost immediately goes what? Low. Goes high here and almost immediately does what? Goes what? Low. Goes high here and almost immediately goes what? Low. Goes high here and almost immediately goes what? Low. So this is E now. So if I come back to what's going on at this level in here, all right, let me just erase this. Here's now how E looks like, because this voltage now was high a moment ago, all right? It's obvious that this is happening fairly quickly. The feedback here just makes this fairly quick. Now, E of t looks something like this. I get a pulse, nothing. I get a tiny pulse, nothing. Get a tiny pulse, nothing. So the average now will not be close to 10 volts. The average now would be much, much closer to what? 0. Or some value. It doesn't have to be 0. Anyway, so the average here will be at a certain point so that the frequency of this signal and the frequency of that signal are pretty much what? The same. And the difference of phase between them is pretty much what? 0. So what we're going to have is that the output of the VCO and the reference voltage will be in phase. So the difference of phase will be fairly, and they would be pretty much what we call locked. What does it mean locked? Well, first of all, their frequencies would be pretty much the same. So one thing is that if this is the frequency of the reference voltage, and this is the frequency of the output of the, the frequencies will be pretty much the same. The second thing is that there would be a difference of phase between them, so that the average of E will be such that if this is 0, this is the average, will be such that this value, when fed into the VCO, will make sure that this one doesn't even drift up or drift what? So we will have this signal and that signal locked both in frequency and in phase, right? This is the reason why we call this a phase locked loop. So the PLL, the phase locked loop, will behave in such a way that the V reference and the output of the VCO will be, first of all, will have the same frequency and the difference in phase will be constant. What does it mean, the difference in phase? How far is one edge of the feedback in relationship to an edge in the reference voltage? And the difference in phase practically constant. Now this we could not care about. This is really what's important. So we say that the phases between V reference and the output of the VCO are locked in phase, right? They will always, if anyone drifts, the other one will follow it. And this is also very, very important. So these two conditions are very, very important. Both of them will be at the same frequency, and the difference between them will be constant. The difference between them will be such that whatever frequency we have in here and whatever frequency we have in here, they are pretty much locked. So this is pretty much how a phase lock loop looks like. Now we know how a VCO really works. It's really not that complicated to build. Now, how about a phase detector? Well, I'm going to give you a very, very simple phase detector in here. All right, so I'm going to take a D flip-flop. All right, this is D, and its D is always equal to whatever VCC is. All right, and its clock is coming from my reference voltage. All right, and this is its clear. This is the clear pin. Notice that it's active high. Right, we can make, if it's active low, we can still work it out. Now here's another one, a D-type flip-flop. It is configured exactly the same. So this is the clear of the flip-flop. This is the clock of the flip-flop. It's coming from V feedback. All right, and its input D is always tied to VCC. All right, and these are our outputs. Now, what do we do with these two outputs? Well, we AND them together. And this one here. This and this are typically, it's fairly easy. We tie these to, this is, say, let's say VCC. So this is a transistor. This is an N channel. This is a P channel. This is the ground. And this is the output of your phase detector. So this is your E of T. All right, I'm going to ignore this part in here. All right, so I'm going to just ignore it. I'm going to just see how the whole thing works. So this part in here, I don't want to discuss it for now. I'm just going to discuss what happens. All right, so this one here, we're going to call it QR. It's Q of the reference voltage. So this is QR, and this is Q of the feedback. All right, so this is QR. And this is Q feedback. All right. Okay. Let's say that this is V reference as a function of time. By the way, this is positive edge triggered, so something happens on the positive edge. And this is V feedback as a function of time. Let's say that they're slightly out of phase. All right. Okay. We can assume that both of these are equal to 0. So when the positive edge arrives in here at this moment, so when the positive edge arrives here, what is the value of D? It's a 1. So QR goes high. We're going to assume that QR starts what? Low. So here, QR goes what? High. All right? Okay. Let's say that this one is slightly delayed. You know what? I need to redraw this thing. Just delay it a little bit. Because it's obvious there that it's not delayed. All right, so V feedback triggers at this moment here. Okay, something like this. All right. We're going to also assume that QF was at what? 0. All right, so QF is at 0. And at this moment in here, QF does what? Because D is equal to 1, QF goes to 1. All right, now let's just drag this thing in here. What value do I have in here? All right, 0. And what value do I have in here? 0. So if this is 0 and this is 0, what am I ending? 0 with 0 and 0. Notice that the clear are active high. So this will not clear that one and it will not clear that one. All right. Now this one up to here, this one is 1, but this is 0. 1, ended with 0 is still what? 0, so we will not clear both of them. Now, at the very moment when this one triggers, all right? The very moment when this one triggers, all right? Okay? The QF goes what? To 1 for a very brief amount of time. So this is equal to what? 1. Now, 1 ended with 1 gives me a what? A 1. And what does the 1 do to both Q's? Well, both of them are driven immediately to what? 0. So QF stays at 1 for a ridiculously small amount of what? Time. In fact, it goes high and practically at the same moment goes back to what? Low. And this one also goes what? Low. All right. And then on the same edge, this one goes high, remains high till this one triggers. All right. And it goes high for a very brief amount of time, and then practically at the same time goes what? Low. So we can ignore these lows. So you can take just this output here, right? You can just take this output and then this is almost like what? QR is almost what? E, but that's not really the way we do it. What we do is that we control 2 transistors, right? And we take the output. And the output, we actually control 2 current sources, but that's pretty much how it works. So if we ignore QF, QF is practically just these tiny spikes, right? So we can say that this here corresponds to the what? Difference of phase between the two. That's pretty much what happens. Now let's just imagine a case, all right? All right. Let's just imagine a case where the 2 signals are completely out of phase and out of frequency. If this is V reference, and this is my V feedback, all right? When this one goes high, and when this one, all right, so this one goes, this is what this one is doing. All right, so triggers, 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 triggers. And this one goes high, let's just say here, and then high here. So it's obvious that they are what? The frequencies are not the same. Now, what would be Q out of the reference, right? When this one goes high, right? Q goes what? High. There's another one. So this is a set. This is another set. And when this one goes high in here, it forces this one to go what? Low. As soon as this one triggers, it goes high, remains high, and now is forced what? Low. And QR is pretty much what? Your error signal. Now, we don't really do it this way. We feed them through transistors so that we can get more juice, because the problem with flip-flops is that they do not output a lot of current. But by feeding them onto 2 transistors that are sitting on top of either one is a P channel, one is an N channel, then we get a lot more current out of it. So that's pretty much what it boils down to. All right, so this is how you can very, very easily build a phase detector. And what you have in here is a PLL. Now you might be wondering, hold on. I know now how it works. I know how the whole thing operates, but what is the point behind a PLL? All right. Well, let me give you just one application. All right, just one application. All right. So here's an application of PLL. Now, you probably, those of you that took 340 or 365, you are. All right. So PLL allows you to what we call synthesize frequency. So PLLs can be, this is just one option, used to generate signals at higher frequencies. All right, so we know that we can generate, we can take a square waveform and then make it slower. But now what we're going to do is that we're going to take a PLL and then generate a signal at a high frequency. Now here I'm going to just show you how we can double the frequency. Right. So let's just take my phase detector. I'm feeding it a reference voltage, VR of t, and remember this is nothing but a square waveform. All right. The phase locked loop is locked when the voltage at the feedback has the same frequency as that one, and their phases are always constant. So notice that they have the same frequency. All right. All right. This is my error signal. Right. My error signal is just a bunch of what? Pulses that we run through a low pass filter to average them. You can think of a low pass filter as a circuit that gives you an average of these pulses. So I get something like this. If this is 0, I get something that looks like this. Right? And then this thing is fed into a VCO. And depending on this value in here, whether it's either going up or what, coming down, the frequency of the VCO, the frequency of the signal coming out of the VCO will either go up or come down. Now we assume that everything is a square waveform. If we take this and then make it run it through a divide by 2, a T flip-flop. So all you need to do here is put a flip-flop in toggle mode. So let's just say this is a divide by what? 2. So we know that the frequency of the reference is the same as the frequency of the what? Feedback. So this is, I just explained how this works, right? So these are equal. We also know that the frequency of the feedback basically is half of the frequency of VO. So the frequency of the feedback is half, right? The frequency of the what? Of the output. Now, if we combine those, right, we can say that the frequency of the reference is half of the frequency of the what? Output. This is this output here. It's the frequency of the signal, which simply tells me that the frequency at the output is twice the reference frequency. Now, this is very interesting. So if we put here a divide by 2, then what do I get? The frequency, I get a square waveform in here and a square waveform in here, and this one and that one is exactly twice. Now, generally speaking, I can put here any number I want. It doesn't have to be a what? It doesn't have to be what? So this is a divide by what? N. So if I replace 2 by n, then this is what I can say. I'm just delete all of these things. So this is 1 over n. This is 1 over n. So what does this tell me is that if I feed here a square waveform, I also get here a square waveform, and the relationship between the frequency of this square waveform and the frequency of this square waveform is that this frequency is n times that frequency. So I have simply built with a PLL system that looks like this. So if I feed it a square waveform at a certain what? At a certain what? Frequency R, what does the PLL allow me to get? It allows me to get a square waveform whose frequency is what? FO. How does this FO relate to FR? Well, FO is simply N times what? FR. Now this is amazingly interesting, and let me explain to you an interesting application of this. Just one simple application. Here's a microcontroller. So this is a microcontroller unit. By the way, for those of you that don't know what a microcontroller unit is, it's simply a computer on a chip. Right? It doesn't have a lot of RAM, doesn't have of RAM and ROM, but it has everything that a regular computer has. Right? Now, we typically clock a microcontroller with some sort of crystal. So we'll just show the, I should not have shown it this way. Let me just show it a different way. Here's a crystal. Here's the symbol for a crystal. And then we plug the crystal in here. Right? And one of these is xtal in or something exn. So one of them is the input, right? This is just to power it. So this one is just to give it power. When you power this, it's a capacitor with a crystal in the middle. The crystal simply does what? Vibrates and generates square waveform. So what we're going to get is that we're going to feed here a certain what? Square waveform at a certain what? Known frequency. Let's just say that my crystal is at 4 megahertz. What does it mean? I'm feeding the crystal where the arrow is a square waveform whose frequency, right? So this is the frequency of crystal. Xtal is the crystal. It's 4 what? Megahertz. Now, from this one in here, if we go into a PLL, then I get what? A square waveform. This is inside the microcontroller unit. So if I were to actually draw a much bigger diagram, this is my microcontroller. So this is the crystal. So I have a square waveform coming out of the crystal. I'm going to call it fx, right? This goes into a programmable PLL. So this is a programmable PLL. And what do I get in here? I get a square waveform, right? That is a multiple of that one. So notice that I have more pulses in here per unit of time than that one. So this is the frequency, let's call it Fs or Fo. This is the frequency of my PLL. Now we just established that Fo can be what? Fo can be just a what? An integer times what? F reference, which in our case is what? The crystal. Now, if my crystal is 4 megahertz, I can make n equals to 1 simply by removing this here. If this one is removed, then the frequency here and the frequency here are the same. All right, so n can be 1, 2, 3, any number I want till a certain maximum value. All right, let's just say to a certain what? Maximum value. I'm going to explain where this maximum value came from. Now, if you make n equal to 1, that means this is what drives the CPU. So this is the signal that goes to the CPU. So this is the clock that drives how fast the CPU. So in our case, if n is equal to 1, the CPU is running at what? 4 megahertz. But if n is equal to 2, then the CPU is running at 2 megahertz. If n is equal to 3, then the CPU is running at 12 megahertz. So if n is equal to 1, then the CPU frequency is what? 4 megahertz. If n is equal to 2, then the CPU, by the way, this n is programmable. By writing some code, you can change it. It's 8 megahertz. If n is equal to 3, then the CPU is running at what? At 12 megahertz. I'm going to continue till maybe n equals, say, 12. This is the maximum. 12. The CPU runs at what? 48 megahertz. So let's just say my CPU can run at any one of these frequencies. So anywhere from 4 megahertz to what? 48. It cannot run any faster than 48 megahertz. Why isn't the crystal inside in here? Or why is this done this way? Well, now I have a complete control over how fast the CPU runs, isn't it? It can run at 4, at 8, at 12, etc., etc. So I have 12 possible what? CPU frequencies. Now here's the funny thing about CPUs. The higher the frequency, the CPU, the more power it consumes. So let's just say I bought this microcontroller and I need an application where speed is not an issue, right? I don't want it to run very fast, but it runs on batteries. So what do? Maybe I would run it at 4 megahertz or what? 8 megahertz. Now imagine if I'm now having the same microcontroller, but now I want to run it as fast as possible, all right? Maybe at 24 megahertz or at 48 megahertz. Why am I running at 48 megahertz? Because I want it to crunch numbers fairly quick. Maybe it's doing some digital signal processing or something like that. Well, the PLL is actually my ticket. So it allows me to say what we call throttle the CPU. What does it mean, throttle the CPU? Control how fast the CPU goes. And remember, the faster a CPU, the frequency at which you run the CPU, the more it consumes power. And the more it consumes power, the faster it drains batteries. I'm assuming that it runs on batteries, right? So there you have it. This is an interesting application of PLLs. PLLs are also used in FM modulator and demodulator. They're widely used in communication systems. I just found this very, very simple case where you can easily understand how the PLL basically allows you to control the speed of, say, a microcontroller unit. Right? It's very simple up to the point, and it shows you what we can do with the PLL. In fact, all modern microcontrollers have a certain crystal going into a PLL before we send this square waveform to our CPU. And this allows us to control how fast the CPU goes. And by controlling how fast the CPU goes, we control how much power it consumes per unit of time. Got it? All right. Well, this is going to come your way. It's Sunday. It's a bit late, but I had a very, very busy Saturday. And, well, it's getting closer to game time. I will send you another video fairly soon. Okay, signing off.